Good morning, everyone. Thanks for coming out to the first Stanford-Berkeley Robotics Symposium, which also has a lot of industry participation, actually. So I want to welcome you all on behalf of the organizers, which are Sachin, Patil, maybe you can stand up, who's been taking care of a lot of the local arrangements. Oussama, Khatib, who's really behind the idea of putting this together. And then myself. So schedule-wise, this is what it looks like. A lot of presentations. We're going to be cutting people off very harshly if necessary. You get a 5 or 10 minute slot depending what it is, and practice will be a little shorter. But since it's such a packed schedule, we have to cut you off. Otherwise, we'll be here till who knows when. We have coffee break in the morning, coffee break in the afternoon, and a lunch break. We'll give you more instructions about lunch, but you'll be on your own. There's a lot of lunch places very nearby where you can go get lunch. In terms of speakers, we have a lot of speakers from Stanford, a lot of speakers from Berkeley, and a lot of industry representation. Anki, Savioke, Industrial Perception, Open Perception, OpenCV, Open Source Robotics Foundation, Redwood Robotics, Hide-Off, Intuitive Automata, 3D Robotics, and Bot and Dolly. In terms of participants, we have 120 registered participants from Berkeley, 48 from Stanford, and 55 from industry. And then, without further ado, I want to introduce our first speaker, Mark Palatucci from Anki Drive. Welcome, Mark.
Thank you very much for inviting me to be here today. I'm really excited about this event, and really want to thank Pieter, Oussama, and Sachin for organizing it. I hope it's the first of many symposiums. Anyway, so my name is Mark Palatucci. I'm the co-founder of Anki, and I think it's a very, very exciting time for robotics. A few years ago, I was in graduate school doing my PhD at Carnegie Mellon, the Robotics Institute, and a few colleagues and I, we had an idea. And one of the things that we realized when we looked around at pretty much most of the work at the Robotics Institute is that it was almost all for government projects, a lot of one-off demos. Obviously, a lot of things were sponsored by DARPA for military or defense applications, but almost nothing we saw went into consumer robots, consumer products, the kind of things that you could buy at Best Buy. So, the obvious reason is cost. If you want to do robot localization and you work in academia, you might run out and buy a $50,000 motion caption sensor, $100,000 motion caption sensor. You get a couple of PhD students together, you calibrate it, and then off you go. But obviously that won't work if you want to put something into a retail store. So one of the other things we realized is that if you look at the price of computing, the price of microcontrollers, wireless chips, sensors, all of this stuff is just plummeting in price. And one of the interesting things is you see a lot in the media, Moore's Law is dead. It's not dead. It's very much alive. And I can go out right now and buy a microcontroller that's 100 times more powerful than the first IBM PC, and I can get it for 50 cents. I can get camera sensors for 30 cents. And because of this, I think it really creates an opportunity to take a lot of the really sophisticated things that we've been doing in robotics in labs for many, many years, and finally, for the first time, try to bring them into consumer products that might be, say, a couple $100 at retail. So we started working on this idea, and it was a nights and weekends project for many years, and now we've grown from a 3-person team with a kitchen table prototype to a 50-employee venture-backed company that is now mass-producing thousands of robots every day. And what I'd like to do today is tell you a bit about our first product, Anki Drive. We announced it earlier this year at Apple's WWDC event. And I could probably talk for a very long time about all the technology that went into this product, from machine learning and image processing, some very sophisticated multi-robot path planning algorithms. There's some fairly complex controls and dynamics. But I can't talk about that today because I have 8 minutes. So what I would like to do instead is tell you a little bit about the mass production process and show you how we actually make something like this thousands of times and have them work almost every time. And that's something that's really hard. It's something that I've learned a lot about in the last few years, and it's probably something that a lot of you haven't seen yet. So with that, I'll tell you a little bit about Anki Drive. So it's a video game that is brought to life in the real world. It's a racing game where you have autonomous cars that are 1/50th the scale of, say, the Google self-driving car. And these cars are very, very smart. They use machine learning, there's image processing, some of the things I just told you about path planning, I'll tell you a bit more. And one of the things we're really excited about is that if you look at physical products, physical entertainment, they're mostly just static objects. They don't really interact with you in a real rich way. And if you compare that to, say, something like video games, where they're adaptive and there's so much interaction, and that keeps it fun and engaging for a long period of time. One of the things we realized we could do is we could use robotics and AI to really bring physical characters to life. And why do you want to do that? Well, what we believe is that physical products, things that you can hold in your hand that are tangible, there's an emotional connection that you have. People can literally fall in love with their teddy bears. So one of the things we're excited about is combining the emotion of physical products with all of the magic that you get from video games to really create an entirely new play experience, a new entertainment experience. So with that, why don't I just show you a quick, let's see if I got some sound here. I'll show you a quick little minute of what Anki Drive is. So that's just a quick look at Anki Drive. And I would love to talk so much about the technology. There's so many things that we're proud of. And all of those cars that you see, there's embedded systems in the cars, but they're also communicating with a smartphone. And there's a lot of really interesting things that happen. A lot of stuff happens on the car, a lot of stuff happens on the phone. They communicate all wirelessly to do some pretty sophisticated multi-robot coordination. But I'm going to skip that. If you want to go into any detail on the tech, grab me at one of the breaks. But what I do want to focus in just the few remaining minutes is what it looks to mass produce a product like this. So what I'm going to show you now is our production line for just a single car that you saw driving. And one of the surprising things is how complex it is. In fact, there are 100 people. It takes 100 people to produce just one of those cars. So let me show you this. the very first thing we do is make our PCBs. You start by covering your PCBs with solder paste. This is an SMT machine that can automatically pick and place all of the components, the wireless chips, resistors, capacitors. After the components are placed, they'll be passed through an oven. Now, not every component on the board can be automatically placed, so we actually have to hand solder a few different things. In that case, that was our encoders for the motors. These are tools. We use tools to do all the injection molding of our plastics. And you create these tools usually by CNC machining or using an EDM process on some of the tougher materials. You carve these molds typically out of hardened steel. There's also a lot of hand polishing that goes into that. Once you have the molds, then you can put them in a very, very high pressure injection molding machine. And in this case, these are little charging cases for the vehicles. This is our tires. You'll see the tires pop out here. And these are multi-cavity tools. So you see there was about 8 that popped out. This is an assembly line for one car. There are 45 different paint steps for each of these vehicles. We paint every one by hand. Now the assembly line, once again, there's about 45 people on this line. We've had to design all of these individual test fixtures and assembly fixtures. Now imagine that there is error that can occur at every single step. So in mass production, largely what you're doing is it's variance control. Your error can propagate over time. So you have to make sure that there's constant test steps along the way. Any one of these things is a failure point. And one of the things that we do is we do functional testing. So at the end of our production line, we have every single car driving. It's very, very important to know what date your robot was manufactured and what production line it came from. In case there are problems that come up in the field, you can then trace it back, and we collect a lot of data. So if there's a failure, we can figure out what's going on. This is the final pack out, and then everything's put into boxes. Those boxes go into crates. The crates go into shipping containers. The shipping containers get sent overseas to into the U.S. We bring them in and we put them bring them into our distribution center, and then they go to physical retail stores. And very excited that after many, many years of work, Anki Drive will be available in a few short weeks in all of the Apple retail stores in North America. So let me share with you just a couple of some of the lessons I've learned in the last few years. Mass production is definitely hard. It's something that just watching that, you can see it takes 100 people to make what looks like a pretty simple vehicle. So the bad news is that costs a lot more than you think. You might carve a mold for a tool, and then you realize that your tolerances are off, and then you have to go and throw it out and potentially start again. There's so many things that pop up, and you're constantly finding errors. You have to track them down. It's very, very hard. The good news is that while it takes a lot of money, there's also a lot of ways now you can finance this type of product development. So a lot of people are using things like Kickstarter, Indiegogo. You typically won't have enough money from a site like that to actually get through the production and marketing of a product, but it's a great market validation, and you can walk into a venture capital's office and say, hey, I just sold 100,000 of these things, now I need to build them, and that's a great way to prove some market traction. This is an important one. Hire people that know what they're talking about when it comes to mass production. As one of our engineers is famous for saying, we don't need people who are smart, we need people who are experienced. And that's very different than something like software engineering, where in software engineering I could go to Berkeley or I could go to Stanford and I can find a phenomenal software engineer and hire that person the day after they graduate, and they'll be, probably an amazing engineer. Mass production, engineering, manufacturing engineering doesn't work like that. You will not find people that come out of college ready to go. You need people that have spent typically decades in factories that know what they're doing. So those people are worth their weight in gold. So if you want to mass produce a product, make sure you find someone who's been through the process many, many times before. So I'm going to show you one last thing. One other thing that you need is luck. So I saw this blog post from a fellow named Jason Roberts, and he says that luck is basically the product of doing versus telling. So doing interesting things and trying to tell the world about it. And the more you do, the more you tell, the better, the more luck that you can have. So I'll leave you with that, and thank you very much.
Our next presenter is Professor Ron Fearing.
Good morning, everyone. Well, thanks very much, Peter and Oussama, for inviting me. I want to tell you about the work we're doing in mobile bio-inspired robots. We're motivated. Oh, my microphone is off. Okay, thanks. Better? So we're motivated by making very, very small robots that will be highly agile and able to go into a really complicated terrain that big robots can't go into, and we want to make them very cheap and disposable. So in case they fail in their mission, we're not going to worry about it because they're going to be disposable. We're very inspired by the mobility of nature. I think we're over the next 10 or 20 years, we're going to get closer and closer to exceeding some of the capabilities of nature, building machines which are faster and perhaps more agile as well. And this chart just kind of examines going from up in the upper left, hummingbird, amazingly agile aerial capability, and down to your ostrich, pretty good surface mobility, and all this space in between where I think if we can combine different modes together, we have a much better chance of building things that really have a unique capability. So I'll show you some of the things we're doing. So we've got a lot of work in we developed in production engineering to be able to make these small robots. I'll go briefly over how we make them. Make them fiberglass, carbon fiber, fiberboard. Typically in the size range here, they're palm size now, thumb size to palm size. A bunch of crawling robots and flying robots. I'll tell you about those. Okay, so we started. One of our first crawling robots was this 2.5 gram crawler. This is made of laser cut fiberglass, folded together. At the time, it was one of the I think the smallest legged autonomous robot. Got kind of limited capability running with shape memory alloy. We've kind of moved on to higher performance machines, going up a little bit larger. But I would say that one of the interesting things on this, you can see that the scale, that just by changing design parameter, maybe changing material, this design scales order of magnitude pretty easily. Probably goes maybe down from a size range of about a tenth of a gram up to 100 grams. So pretty good size range, about a 3 orders of magnitude in weight.
Still working on with that. I want to check that out.
Okay. So probably didn't hear anything I said, but you saw the pictures. Okay, so our process is actually pretty simple. We take a laminated process and laser cut. The laser cuts form a joint. The manufacturing is the easy part. Actually, the design is a hard part. That's still a pretty interesting open question. How you go from a conceptual design like this to a full design like this. This is Andrew Pullen's robot, and it's done with basically a flat planar layout. You get these parts that are laser cut. They incorporate both the joints and the structure, and this goes through the process here. Here's the full design, starting with the various pieces of the chassis, top and bottom. They're folded, combined together, and finally you end up with a complete chassis. And there's your robot. This is a robot with minimally actuated, one motor for the left side, one for the right side. And we actually get It's not the most complicated robot, but we start to see you can get some pretty interesting behavior out of it. They've got a very high power to weight ratio because they're very, very lightweight structure, and because it's minimally actuated, all the motors are, most of the time they're running, they're providing useful work for you, and so it can pretty dynamic. So we think the dynamics is going to be really interesting for these small robots to give them mobility, and it'll get there. It'll get there. Okay. Well, it really wants to get up there. Okay, there you go. There you go. So it made it. Oh, that's some problem at the other side, but it got up there. So we're saying we're really inspired by the amazing capabilities of animals. Worked very closely with Bob Full. So the example here is a really interesting escape behavior. The animal gets to the end of this ledge, and it just swings around, uses its kinetic energy to carry it through. And so we're really interested in, well, how do we understand that, and how do we capture that? And we can do similar things with our robots. They just catch at the end, and the forward momentum causes them to rotate around. Okay. So dynamics is really important. We think the more dynamics, the better. But you have to worry about sometimes things get a little too dynamic, and how do you control all this energy that you're putting into the system? So here we've got, you can see a robot with a roll instability. So the control issue has to come in. And one way to take care of this is with a wing structure. Now the wings are providing both forward thrust and some damping moment. And you actually don't need the wings don't actually need to be moving, because as the robot is running fast enough, it's generating its own drag forces, and these drag forces will provide stabilization. You can see here in Duncan Haldane's Velociroach robot, these passive wings on the side, they're not moving, but they are providing a stabilization drag. The speed on this robot was limited by the stability. Without the damping of the wings on there, it would roll over like you saw on the previous slide. But this robot will run at 2.7 meters a second, and until last week we were, I think, tied for second fastest legged robot, but now we slipped to third because of the Wildcat. So this is the third fastest legged robot in absolute terms at 2.7 meters a second. Okay, so that's running. Running's, of course, an important capability. We also want to be able to maneuver. So maneuverability is going to be limited by the traction forces you can get with your feet. If you're trying to run on ice or other slippery surfaces, it's going to be really hard to turn. How many minutes do I have left? 3 minutes. Okay, we're in good shape there. Okay. So one way to get really high turning moments is to put a tail on the robot and use the dynamics and inertial forces generated by the tail to get the rotation. And this is work by Nick, who's now working with Mark Kokoski at Stanford. And you can see we get a turning radius now of 4 centimeters. It's running. If you looked there, it looked at the traction forces that were required on the ground to cause that turn to happen at that speed. It wouldn't happen. So it's being caused by the tail. And you can put a servo around the tail so you can stabilize it with a gyro and control your heading. Okay. So coming back to aerodynamics, well, we can turn with inertia forces. You can also turn aerodynamic forces. Nick's going to present this at IROS next month. So it's running, and the tail is going one side to the other, and there's enough drag force generated by that tail that will cause it to rotate one side or the other. And we did the control case, of course, where if you take the tail with no aerodynamic surface on it, and it won't turn anywhere near as well. So it's turning by just the rudder effect of the tail. Okay. So a hybrid. Let's look at legs. So we had legs and aerodynamic tail. Let's come back to legs now, legs and wings. So this is a hybrid robot with flapping wings and legs. So now you've got the mode. Well, flying is very expensive. Takes a lot of power. So if you've got the opportunity to use your legs, that'll be more efficient, give you better durability. Sometimes you have big obstacles, though. So you need to be able to climb up with the wings. And here, coming up a 70-degree slope, if you look closely in the picture there, you'll see that, normally when you're running along on the ground, you lose contact with the ground. But here you're running up the wall, you're losing contact, and the wings will force you back into the wall so you can maintain the running. Okay, running out of time. You can do. One of the things we're interested in is multiple robot control, so you can distribute the intelligence among the different robots. The flying robots, they're about 13 grams. They really, even today, they can't carry much processing capability, mainly because of the power requirement. So you can distribute the intelligence and have one mobile robot that's looking at the flying robot and telling it where to go. Okay, so climbing, back to climbing. We're very interested in this concept of all-terrain mobility. So we want to have something that's as capable as an animal is of climbing, whether it's a floor, a wall, a ceiling. And so to do that, we have to understand how do we adhere to surfaces. So we've got a lot of interest in understanding adhesion, again, working with Bob Full on coming up with ways to build adhesive mechanisms that run at very high speeds. These legs are going at about 20 hertz. And we want to be able to work in dirty environments. So that's actually the limitation. There's a lot of great adhesives out there, but how do you climb in a normal environment where it's covered with dirt? The typical adhesive material is very soft, and it's going to get all cluttered with dirt. And so we're working on special new types of adhesives. Polymers, they get dirty. After you take steps, they clean up. So, to conclusion, this is where I want to be able to build a robot that's as capable as a squirrel to keep us busy for the next 20 years. So, thanks so much.
Thanks, Ron. Our next speaker is Francois from Stanford.
Okay, thank you. So in the next few minutes, I'm actually going to give you an introduction of some of our work in computer haptics and simulation that we're doing at the robotics lab at Stanford University. So some of the ideas of haptics, for those of you who are not familiar with it, is to try to explore use the sense of touch to actually work and maybe teleoperate robots or work in the digital world in simulation and see how we can actually use this to kind of create a more intuitive form of interaction. Now, to motivate what I'm going to show you, I'm going to start off with actually one task, which is one of a watchmaker. And this is a kind of a very fine task where you use the sense of touch to do very fine assembly of parts. And that's been actually done for actually several hundred years when we've assembled those fine mechanisms. But more recently, when we designed them, we use kind of sophisticated CAD tools. And if you do maybe any kind of mechanical design, it could be a huge aircraft, an engine, or a watch, designing it is one thing, assembling it is another. And often a lot of those tools don't tell you if you're going to be able to assemble it and actually how much time it's going to take to do this. So imagine that we started with a watch, but what we would like to do is really try to assemble it, designing it and then assembling it. And if we're looking at the components in there, well, obviously we're going to want to have some way of modeling, and there's a lot of this in computer graphics on how we can create 3D models. We're going to be very interested in taking those parts and have them interact together, collide, not just having them penetrate or intersect. This means looking at collision and possibly adding some dynamics. The haptics in there, the idea is to now take those parts using a haptic device, which is a small little robot that can recreate forces in your hand, and be able to control those different parts in the environment, as if you were doing a virtual assembly. From there on, what I wanted to show you is, well, if you want to create a simulation like this, what do you actually need? And some of the work actually has been done a lot on haptic devices. And to go back, well, if you actually want to look at when haptic devices really started off, we can go back to actually the 50s. And that's when we started to build telemanipulators. But it's much later in time, actually, in the 90s, with Silicon Graphics came up with computers that would allow us to do 3D computer animation, 3D imaging, that we could start to really combine haptics with simulation. And so the devices have improved a lot in recent years. And we don't just do now point contact haptics, where we just take a finger and touch a surface. We have the ability now to actually feel torques, forces in rotation, forces in translation, and even grasping. And this opens up really some interesting capabilities where we now have to start revisiting the whole haptic simulation framework. What are the algorithms we're going to use? It's not just single point contact, but what we want to do is be able to take complicated parts, come in contact together. And this means we're going to have not one, but tens, hundreds of contact points. And so we'll have to come up with ways to very efficiently compute those forces. Now, one of the biggest challenges that happens when you work in haptics is that you have to solve this problem of collision detection. And in computer animation, you need about 20 to 50 frames a second to get a good animation. To get a good haptic rendering, you need 1,000 update rates a second. And so there's no shortcut. You have to compute those collisions very fast. So what we've done is revisited a lot of the work done in computational geometry and parallelized this on computer graphic cards. And so this is to show you a bit of the result of what we're doing today. We're now able, with those haptic devices, to take those complicated parts. Those are parts that come straight off a CAD tool. This is like SolidWorks. We're able to import them. Those tools have tens, 100,000 polygons each. You can now compute those interactions in real time. You're feeling them as you assemble them. So you can kind of create very intuitive interfaces to interact with those environments. Here again, taking apart, doing an insertion. So you're feeling compliance as you are interacting. You feel every teeth of the gears. You can line up parts, center them. Here's a slightly more tricky part where you've got like a small rectangle, modeling screws, and so on. And so where we're really wanting to go with this, great. So as we're zooming out, so where we're really bringing this is to coming up with new tools. Great, thank you very much.
Thanks, Francois. Our next presenter is Professor Ruzena Bajcsy.
Okay, so first 30 years of my life I spent on robotic perception, strictly robotic perception. At the last 10 years since I came to Berkeley, I sort of said, okay, I'm going to spend my remaining active times on observing people because after all, what you make robots are for people, to help people, and not just robots for sake of robots. So I prepared, I have 10 minutes, correct? Okay, I will try to do that. So anyway, you cannot do this kind of research by yourself. So I have all these collaborators. And so what is the problem? The problem is observe, monitor people who engage in physical activities. I shy away from the cognitive part because I cannot crawl into your head. And I really believe what I can observe. So physical activities I can observe, and I can really apply all the robotic technologies that we have developed over the past 40 years to this problem. So I am interested in model their behavior and design proper feedback. And this is the critical thing, feedback being either robots, avatars, or real human coaches. The feedback can be immediate as you are exercising or towards long-term change of behavior. Model the performance of the user either for assessment, which is in the physical therapy, for example, or improvement of performance like you have in athletics or, for that matter, any exercise. So our goal is to design multimodal. As you know, I don't believe in one sensor can do it all. Observational systems aimed primarily for elderly, since I am one of those, that perform robustly, easy to use, respecting privacy of the user, which is a big deal for when you deal with people, that how much information are they willing to share, yet provide sufficient information for the health provider to assess the current conditions in order for them to give the appropriate feedback. The system must work locally, but also in remote sensing, and networking is really a big issue in this problem and must be sensitive to individual needs. All right, so what tools we have available? In principle, we can bring people to the laboratory clinic for calibration purposes because every human is different, so you need to calibrate. You know, what is your strengths, what is your reach, how far can you reach. given some physical activities, task, we can observe them via motion capture, force, accelerometer sensor, EMG for measuring the muscle stiffness, and some others. Based on these measurements, in these days you can measure through very simple measurements for example, heartbeat and some other physiological parameters. Based on these measurements, we can extract kinematic and dynamic parameters needed to build respective models, hence obtain baseline for each individual. This is the key, folks. You have to respect every person is different. Okay. So tools for remote telemonitoring in home, one needs to consider devices which are space constrained, cost-effective, easy to connect to internet or wireless technology. We work with Kinect. Kinect requires a certain distance. Not every old lady has an apartment which has that distance. So those are the practical difficulties. All this is available, however, the design of interfaces must consider the cognitive and physical limitations of the elderly user, forgetting to charge the cell phones, for example. The overload effect of the display. You have to pay a lot of attention, and this really brought home, as we have performed these experiments, that the display, you have to have large letters so that people can read them. You have to have not too much clutter, effect of display, proper size of the letters on the display, etc. The reduced cost of the devices also has effect on the accuracy. As you know, Kinect is not the most accurate sensor, so you have to deal with that in your assessment. So this is one example that I picked from several of our projects that are ongoing to, I have a misspelling, health project, data collection. So anyway, what we have here is that we have 10 exercises. Each exercise is repeated 10 times, and you can see here the list of exercises. So here is the computer-assisted coaching system. You see so you start with the program start welcome screen, then you have the exercise selection, which one do you want, and then you have pre-recorded demonstration of the video, and the subject performs exercise automatic evaluation, and then you receive summary exercise of the past performance. And one of the questions is, how do you evaluate it? How do you score? What should the scoring be? So here is the Kinect skeleton. Is quite noisy. Extract higher level motion features, filter them with moving average filters. And you can see on the right side, right now we have these displays where it tells you whether you are reaching the proper goal or not. So what we have is each exercise emphasizes a different parts of the human body. So heel drags exercises the reach, lateral steps, angle, cross leg, etc., etc. Okay, so here is our coach in Oregon, and she is showing you how to do the cops and robbers, okay? And I was not very good, as you will see from the data. So here is 2 subjects. One of them is me, okay, on the left side. And you can see that I am not doing too good. At that time, I had some problems with my joints, so I was not reaching far enough and doing the proper exercises. Okay, so then the beauty of this is that you can really measure more detailed, the angular changes and apply all your knowledge from robotics on this problem that you can evaluate more detailed than so far people have done. So here is the arm reach measured with respect to transfer horizontal plane, and here is a shoulder rotation measured in sagittal plane. So that's what, and you can do the same thing for your legs, and so forth and so on. So here is some data that we have. And one thing you should notice that both for me and for the other subject, as you repeat these exercises, you are improving. That's the third diagram there. Okay, so what should be the overall exercise measure and score? Well, here you have the red is the forward reach, and the blue is the shoulder notation, and we do represent the exercise with numbers such as maximum reach. We measure the maximum reach, and maximum rotation results in extreme abstraction, but the data is much more richer, so the scores are not, this is not enough representative or informative. So we can do more detailed measurements. And so what are the lessons we've learned thus far? Limitations of the imaging technology. Now, the new Kinect presumably is going to be a bit better and more accurate, but requirements on the household space. You know, the Kinect right now requires, I think it's about 4 meters space from the camera where you are doing the exercise. And as I said, we found that not every elderly person has such an apartment. The video presentation and the choice of exercise in the form of interfaces and feedback. This is still an open problem. Folks, those of you who are students here and looking for PhD, I mean, if you are looking for a challenge, this is it. How to model the feedback must be simple, hard to recruit many subjects, how to organize the database. Okay, so measurement difficulties. We do not have direct access to measuring the axis intersection on human body. So, for example, some of the biomechanics folks, they drill a hole, something, in order to get the actual axis. All right, okay, sorry. So they drill that, and you can't do that. So anyway, so here is just an example of the same exercise, 2 different subjects, how the measurement moved. So you make these errors. Okay, I can't tell you everything, but anyway, conclusions. The working with people is hard. The problem is important because my generation is growing, as you know from all the statistics. So the opportunities to help that generation to live independently and meaningfully is here, and technology can help. But as I said, the problem is hard. Sorry, I have some videos, but if you are interested later. Right?
Thanks, Ruzena.
Okay.
Our next presenter is Steve Cousins from Savioke.
Oh no.
Savioke.
I know, it looks like karaoke. This is what happens when you try to create a new company name and you give yourself 3 hours, time box it. We need a file for incorporation now. So I want to talk briefly about service robotics, and I won't say a whole lot in technical detail today. I see a lot of friendly and familiar faces in the audience. I spent the last 6.5 years at Willow Garage and trying to create what we thought was the basis for the beginning of a personal robotics revolution. And it was an exciting time. A lot of interesting stuff happened. Probably the most exciting thing that happened out of that was this project we called Robots for Humanity, which was a demonstration of using a service robot to help somebody. And if you think about older adults and the problems that we're going to be seeing in the future, here's a guy who at age 40 had a stroke, became quadriplegic. He had been the CFO of a Silicon Valley company, and suddenly he can't speak, he can't move hardly at all, he can only move his head and a little bit of motion in one arm. And with that, he's kind of stuck, right? I mean, that's sort of the extreme disabilities. He sees a PR2 on TV and says, wait, that can be my body, and asks us to build him an interface. And long story short, we build him an interface so that he can start to play with the robot. Now, it's a great story. It's a heartwarming story. The first thing he wants to do when he gets the robot is turn it on himself, which is scary. and scratch his itch, right? He wants to scratch an itch for the first time in 10 years. That's really cool. He's used it. We've had the robot at his house. He's gone up. He's done gone across his house to a drawer, opened it up, gotten out a towel, brought it back, wiped his face with a towel, and so forth. He actually shaved Charlie Kemp of Georgia Tech. Charlie was in Atlanta, he was in Palo Alto, and he shaved Charlie remotely using Charlie's PR2. So lots and lots of cool stuff, right? Except for one big problem. That's a $400,000 robot. Henry can't have his own robot. Nobody else like Henry can get one of these robots, and that's just not a situation. So for the last 2 or 3 years at Willow, and now going forward with Savioke, I've been on kind of a quest to build robots that can help people at a much more affordable cost. If you look at just Willow Garage and what happened, Willow Garage had a bunch of spin-offs over the last basically 2.5, 3 years. The top 3 are actually have products out or are in exit, as we say in Silicon Valley, in a good way. Actually, it's funny. I see Melanie's here, and Unbounded, when I first did this slide, came up in white, and they're in stealth mode still, so that was appropriate. But I turned it to black so you could see. I think there's going to be a talk later from Heidoff. And 3, I think we have a talk from OSRF. So a bunch of spin-off new companies came out of Willow Garage, and I'm really, really proud of that. But what I want to do is just for a couple minutes talk to you about where I see Savioke going and how I think we can impact the world of service robotics and why the time for that is right now. One important lesson from Willow Garage, and so I'm thinking this kind of as a retrospective, is that over the 6.5 years, one of the things we did was focus on open source. And open source has some really interesting and maybe unexpected powers. The biggest one is it gives you an incredible recruiting advantage. Right? So when you go off and you're a graduate student, you're going off to work at a company for the summer, you want to do an internship. If you go to a company that says, I'm not going to tell you who you're going to work with. When you're done with the summer, we're going to own everything you did. But you're going to learn a lot, honest, right? You may go, and it's not bad. You're going to get paid some money. But wouldn't it be better if you go to a company that says, whatever you do is going to be an open source. Here's who you're going to be working with. Here's what you're going to be working on. You're going to take maybe what you were doing in your thesis, continue add it to the open source community, and when you come back, you'll take not only what you did, but you'll also have access to what everybody else in that community has done, including a bunch of other smart interns. That program and sort of that example was incredibly powerful in terms of setting the stage, because we were able at Willow Garage to get a lot of really smart people through. 130 interns came through Willow Garage in 6.5 years, unique interns, and there was more like 200 internships. And shout out to Melanie for running that internship program for a lot of the years. The other thing about open source, though, is that it makes it really easy for you to take the ideas and the concepts that you were working on before and move them into the next company, right? So when you've worked on something in open source, the next time you can go forward. Now, from a company's point of view, this may or may not be a good thing, right? Oh, all my ideas can go wherever. But from if you look at Silicon Valley, and one of the powerful things about Silicon Valley is people moving from one company to the next and creating and reforming and great ideas becoming real. And open source is like a lubricant for that, right? It means that you don't have to worry about what can I take? Oh, I have to re-implement this thing that I did before. There's a lot of stuff out there that you can basically pick from, a lot of it that you did, right, when you move from place to place. And so part of the story here is that open source has made a huge difference in setting the groundwork for personal robotics and a service robotics industry. So I'm defining service robots as robots to help people in human environments, right? So help people is important. There's a lot of robots in human environments that are designed to do non-helpful tasks. For example, entertainment tasks. Not that it's not helpful, but it's not at human scale. And human environments as opposed to factory environments where you can really control things, right? So if you want to have a robot moving around in a human environment, it's possible to put tape down on the floor, but it's not always appropriate, right? And so you have to basically solve the problems of understanding. And what's interesting is that we're now on the cusp of, I think, solving these problems for a couple of interesting reasons. So So why service robotics now? Open source I already talked about. That's a big piece of it. The second one is cheap, powerful processors, right? Moore's law, as the first speaker said, is, it's not dead, right? Moore's law is cool because it keeps on evolving, right? We keep on changing technologies that let us continue to pack more and more functionality into smaller and smaller packages and get them cheaper and cheaper. And the best example of that now is cell phones, right? And cell phone processors are doubling in speed, just like computer processors have done for the last 30 years. The other thing is that also in the silicon space is sensors are getting much, much, much better. So the Kinect from Microsoft that we just heard about is a really powerful processor and is the kind of processor, when we started the PR2 project in 2008, we built this entire head, and if you've seen the PR2 head has this 2 stereo pairs and a long-range camera and a projector, and all that is thousands of dollars worth of mechanism in order to get you 3D view of the world. And somehow, PrimeSense in Israel plus Microsoft are able to get that down to a $150 package, which makes a huge difference in terms of what you can do in a robot and the cost that robot's going to be. And that hasn't ended. The Kinect is not the end of that story. It's the beginning of the story, and those sensors are getting better and cheaper, and the software to go with them is getting better. And so what all that adds up to is what are going to be cheap and capable robots in human environments. And the important thing, cheap, capable robots make business sense, right? Business sense means that you can afford, and why do I care about business? I started with this kind of humanitarian story about service, and we want to help people, right? I care about business because, at Willow Garage, I could afford to give Henry a PR2 robot, $400,000. I could give Henry and, a few of his friends, right? That's it, right? That's the end of the world. That's the amount of impact that you can have. If you can't sell the product, then you can't scale it up, right? And so somehow you've got to make something that's valuable enough that people can afford to buy it. So once you get the cost down, there's a huge step function. If you take a $400,000 robot and you try to figure out what's the hourly cost of that robot, right? You can do the math, and based on how many assumptions about how long it is, you're talking about a robot that costs something like $70 an hour, right? You can hire a lot of people for $70 an hour and get them to help out in a lot of ways, and they're a lot less clumsy than a PR2. But if you get a robot down around $20,000 or $30,000, all of a sudden you've got a robot that's interesting because you can't just afford to put a person in necessarily to fix it. And if you put it into a job where it's doing something that's mundane, that's boring, that people don't want to do, the classic robotics, dirty, dull, and dangerous, all of a sudden you've got a recipe for something that's really successful. So I think that's all I have, yeah. So with that, I think I'll finish on time for Peter, so he doesn't have to interrupt me too bad. And thank you very much.
Thanks, Steve. Our next speaker is Stephen Miller from Stanford.
All right. Hi, everyone. I'm Stephen Miller from Stanford University, and I'm here to talk about clean models from noisy sensors. Okay, that was a dumb joke. So, sorry, Francois. But the standard introductory spiel that I have to give you is that this is what robotics used to look like for a while. You pay $100,000 and you get a really nice laser, you get a PR2, and it's great. Now for about $100, you get a sensor and a dancing game to go with it. So we've come a long way. But the big problem here is you get what you pay for. So this is a view of my lab mate from face forward, and it looks okay, right? It'll be almost like a photo from the right viewpoint. But if you look from above, you're going to see that that flat wall behind is really thick and noisy, and even curved. And we can quantify this a bit by looking at a flat wall. And as you get further and further away with the Action Pro Live, it just gets worse and worse. So the joke, which never works, is that sensor calibs frail at distance, XBL is atrocious. Someday someone's going to laugh. But so it turns out the calibration helps. So I'm not here to really talk about this today, but a plug for an RSS paper. So we can improve the data a little bit, get rid of some of this warping. But of course, nothing's perfect. So this is a point cloud you might get if you walk around a room and register everything together. And honestly, no offense to Roddy, but point clouds are a little ugly sometimes. So what's been gaining popularity lately is volumetric reconstruction. So Kinect Fusion came out right after the Kinect. Continuous was an extension from John Leonard and a few other people. And in PCL, we have implementations of it too. And so what this does is you move around the camera, and it leverages multi-views to try to get a nice, clean model out. So the data you have to start with are going to be these discrete points, basically, different views of the same object, with really no idea of how they should line up together. And so these methods do online alignment usually. And so what that means is it's going to get one view. It should be a noisy point cloud, not a nice slice of a PR2. And then the next time the camera comes, it's going to try to line it up and register together. And as you keep integrating views, you're going to find that you get a decent reconstruction, but there's this drift problem in the middle because you've done this all online. Another problem here is that these all assume zero mean noise. So they average out the noise and hope that you get a clean surface out in the end. But like I showed you before, zero mean is maybe not the right way to capture this. And even calibrated, you're never going to get perfect data. So our paper, the first insight, which seems pretty obvious if you have an online method, is to add loop closure links. So now instead of just doing this pairwise alignment, add links in between and do a graph optimization. The second insight is to use a non-rigid alignment to try to actually warp these things into shape, correct for the fact that the data is not perfect coming in. But we'd like to keep it as rigid as possible, and that's from a graphics paper from about 10 years ago. So that's the very high-level idea. I can't go into the math, of course, but I'll show you pictures instead. Instead of this, you can get something like this from the same data. And this is work done with Shenyu Zhu and Vladan Koltin. So to recap the main idea, Kinect Fusion gives you a nice smooth surface, but without loop closure, it's going to break. Calibrated data can help you a little bit. So you can see here that even just not having as much of a warping helped it stay on track with this online approach. But if you're willing to add loop closure links, you can get quite a bit better. And the screen maybe isn't even high-res enough to see that there actually are breaks along the side. So this still is not a perfect reconstruction. And then if you add this non-rigid or elastic term, you can get something really nice and cohesive. And this was from walking around a couple times. So that's the basic high-level overview. So this is going to be at ICCV. So come check that out. And then if you want to calibrate your sensor, we've got data online. So talk to me after. Thanks.
Our last speaker before the break is Professor Claire Tomlin from Berkeley.
So I'm going to talk a little bit about our research in robotics and multiplayer games. We've been interested for a number of years in systems in which the control authority is shared between humans and automation. And we're really interested in designing automation for such a system. So automation that works well in such an environment when you have to interact with people. We've built a number of, so as we know, Ruzena presented this quite well. It's a very hard problem. And so we decided to approach it through a number of kind of structured problems or test beds. And one of the test beds we built, or we're working on, is one which is inspired by this capture the flag game. Basically, you have two teams, and each has a flag, and you have your home area, and the flag of your opponent is your goal. So you'd like to capture the flag and return to your home area without being tagged by your opponent. We thought this might be a kind of a good litmus test for teaming up humans and robots. So imagine teams now that are people and robots at the same time. And the advantage here, our robots are quadrotors, is that the quadrotors can provide bird's eye views in areas, look at where the opposing team members are, look at where the flags might be, because that's unknown information to begin with. And it's an interesting problem. There's a lot of unobservability. These games are often played by undergraduates on university campuses, as I actually learned the game when I was a professor at Stanford from Stanford undergraduates. So one of the tools that we've been designing for working on this problem is, we'll call it a reachability tool or a backwards reachable set. And so we think more generally, instead of just thinking about games where we have teams of players, so opposing players, we'll think about a control system just modeled by a differential equation where there's a set of control inputs U and a set of disturbance inputs D. So they're playing against each other, and you'd like to design a control that works in the face of worst-case disturbances. So that's how we sort of think about framing these problems in a game theoretic context. And so what we're computing here are all states for which, in this case, for all possible control actions, a disturbance D could push you into that unsafe region, that red region, in time t units. And so we can solve this problem. It's typically a computationally intensive problem by solving an appropriate Hamilton-Jacobi equation. We can turn the problem around as if you want to achieve an objective, and you'd like to do that in the face of worst-case disturbances. And so here, it's just basically the same problem, but now the control is trying to get the system into that blue set in the face of the worst-case disturbances. And then you can take these constructs, these sort of sets, and do set calculus on them. You can look at the set of states which will reach one set while avoiding another set. And so it's a very neat framework for dealing with constrained control problems where you have different disturbances and different control inputs, and you'd like to be able to solve these. And so we've been thinking for a while now about hybrid systems. So think about a hybrid system now where you have, again, continuous dynamics, but you have a number of different modes that the system could be in, say K modes. And if you just sort of zoom in on one of those, you have the possibility of not only sort of controlling the system through continuous inputs, but also, hitting buttons or changing modes in the system, which causes you to switch behavior. So we think about these sets as a kind of reach-avoid operator. We'd like to be able to compute regions which reach one set while avoiding another set. And that other set could be a transition to a mode in another state space that you don't want the system to transition to. So you get a kind of beautiful interplay of continuous and discrete dynamics when you look at these kinds of set calculus. Okay, so one thing that we did with our quad rotors, just to demonstrate this on a single vehicle, is a sort of high-performance switch maneuver where we're asking the quad rotor to go through 3 different modes. Well, first of all, it climbs up, so in case we screw up, it doesn't hit the ground very quickly. It goes into an impulse mode, and then it quickly turns around to a drift mode where the rotors are switched off. That's when it's upside down, and then switches into a recovery mode. So we can kind of use these sets to chain maneuvers like this together and actually synthesize switching policies. Okay, so back to capture the flag. This same methodology can be applied. We're looking here at a 2-player game. It's 2-player played in the plane, so there's 4 dimensions. We're just looking at control inputs, which are velocities. And so we're computing 4-dimensional sets. What I'm showing here is a 2-dimensional projection of those. So we're fixing the attacker. The attacker is the person who's trying to get the flag and come back. We're fixing his position, and we're asking what are the winning states of the defender. So those are the kinds of things we can compute. And this can be computed. So this is a 4D Hamilton-Jacobi equation. We can compute that now in real time. And so we can compute the region for capturing the flag F and the region that the defender has to be in order to defend against returning back to the safe region. We can compute the composite game. And so we did this, and we then applied it sort of in the framework. This is without the quadrotor right now, in a scenario where we had people playing. This is on the Berkeley campus, and we computed these sets, and then we displayed the information to the players who were carrying smartphones. So you can see that. You can see that this provides some kind of intuitive information. So this is what's being displayed on the smartphone. These are the 2 players. This is the attacker who's got the flag and the defender. This is the winning region for the defender. And the attacker's just got the flag and he's trying to go back to his safe region. So it's determined by the initial conditions here because the defender is outside of his winning set initially. So that tells us that... if they both play, if the attacker plays his optimal strategy, then he'll be able to get to the safe return region. This is interesting, though, so he gets to the return region. It's a little jumpy. You can see him saying, I won. But you can use these sets now to do some interesting things. So we took the smartphone away from the defender and asked, this looks like kind of an easy game. What would a person just do naturally? And our attacker still had the smartphone, so he had access to the displayed information and the winning sets from that game. And you can see that the defender initially started in a winning configuration. But the attacker, in this case, has played a few times and knows that the defender doesn't have the smartphone. So he plays suboptimally. And he does this while looking at the sets and looking at what the attacker's doing. He plays suboptimally. It gets the defender to do something that's also suboptimal and gets him outside of the reachable set. Okay, so we introduced the quadrotor now. So again, this is the Berkeley campus. And now we can do all sorts of interesting things. We've got an attacker who has the flag. This is actually the flagpole on the Berkeley campus. And he's also controlling a quadrotor. And then we have a defender somewhere up here. So we don't only have winning sets for both players, but we can compute things. Okay, so those are the positions. The attacker goal is up at the top of the screen there. We can compute, as we have, the winning regions for both of them. And you can see that the tools that we're using allow sets that are disjoint. So the defender winning region is disjoint because of the presence of these buildings. But you can also use this tool to compute visibility regions. So if the defender stays outside of the attacker visibility region, well, the attacker doesn't know, he can sort of hone him down to a region, but he doesn't know exactly where he is. But this is interesting. If he's using the UAV to try to get more information from that scenario, he could guide the UAV to go to not just look at the complement of the visibility region, but the complement of the visibility region that's also his winning region, so the intersection of those sets. And so that's basically what it does. It's an automatic algorithm which will guide the quadrotor to basically to search in a fairly standard pattern over this intersection of those sets. And so this is just one play out of that. You can see the viewpoint from the attacker with the flag, and also basically the data showing where the quadrotor is. Okay, it's a little jumpy. I'll show these after if anyone's interested. Okay, so then finally, now that was a two-player game going to multiplayer. So what's interesting here is that once we have the 4D solution, so we don't have to go up to any higher dimension. We can store that solution and then use it in a multiplayer game. So what we have is basically the same game, but we use a graph matching method to basically compute the worst case defender-attacker pairs and then solve the game for the defenders. Okay, I think we're running out of time, so let me just conclude to say we've been spending quite a lot of time computing and using this reach-avoid operator for specifically what I showed was winning sets in dynamic games, but more generally we've been using them in control problems where the players are uncertainty or disturbances pitted against control. Algorithmic development, so the tools we developed are part of Ian Mitchell's thesis, and he's developed a level set toolbox. That was the sort of set calculus that I showed you. And we are computing new methods for automating the reachability under switching and new methods for doing this in high dimensions. So currently, things that we've been doing are combining this set calculus with machine learning to do high performance control within the reachable set. And also, as I mentioned at the beginning, trying to think about how to design automation which works well when you have control authority shared between people and automation. Thanks.
Thanks, Claire.